welcome grade 12s. Today we're going to do a section which sometimes you really like, sometimes you don't like, but we're going to break it down for you. We're going to start with some of the easier stuff today. We're going to do it over a couple of weeks, and that's work, energy, and power in your books. That's the heading it's under mechanics. Today we're actually only going to look at work and energy because we're going to make it a little bit simpler today, or work energy is a better way to put it, okay? But before we do any of this, it's important that you know the terminology. So there's a couple of terms I want you to discuss, and what I'm going to give you a couple of minutes to discuss in a second is the concept of work, network, and the work energy theorem, because that's really important, okay? They're very, very important. So I'm going to give you 2 minutes, and we're going to see how far you get. So you've got 2 minutes, and your 2 minutes start now. Well, grade 12s, how did you do? Hopefully there weren't too many arguments about the concept of work, which remember when you got first taught that in grade 9 or 10 or whenever it was, I know when I teach my learners, they look at me with big eyes and go, oh, you mean I don't do work when I carry my school bag around to school? The answer is no, because work is very specific in science. It's not just general work like we use the word in English, okay? So what we're going to do quickly is I want to give you an overview of work, energy, and power as a section. We're not going to cover all of this today because it's just too much theory, and we want to first cover the first parts that are important to start off with, and then once we've built a foundation, we can do the rest, okay? So the first thing we're going to look at is we're going to look at the whole concept of work, and what does it mean to do work in science terms, not in general terms, and look at the equation W equals F delta X cos theta, and we'll deal with all of that together. Then we're going to talk about the work energy theorem, and grade 12s, I can't even begin to tell you how important the work energy theorem is. I am going to guarantee you a question on the work energy theorem. Whether it's directly work energy theorem like we're going to do today, or whether it's got to do with the non-conservative force will depend on the question, but they're both very closely related. Okay, so we're going to look at those. Then energy is important. We're going to look at the law of conservation of mechanical energy because it's quite important. And we're going to differentiate between normal energy and mechanical energy. And then, of course, remembering that mechanical energy is both kinetic and potential. And non-conservative forces and non-conservative work has a lot to do with mechanical energy and whether it's conserved or not. And then lastly, we are going to look at power because that's quite important. And here we're going to look at power ratings, and one of the things in your curriculum, it's one of the weirdest things, is the thing they talk about is how much power it would take for an engine, for example, or a pump to bring water up from a well or from a storage dam or something like that. So that's quite important, okay? So let's just get down to the nitty-gritty. Today we're just really looking at work, network, and work energy theorem. Next week we're going to add in non-conservative force and look at the conservation of energy and do a little bit of power, okay? So first of all, the definition of work. These are the sort of things that you learn, okay? So hopefully you all got this, and we know that work is defined. Work is defined. There we go. Oh, look, I'm putting extra little things on our thing because I can. Let's just get rid of it. There we go. Work is defined as being done on an object, or when a force is, the work done is the product, so it's multiplication of the force of the displacement and the components of the force parallel to the displacement. Now, this is quite important because what we're saying to you is we need a force, but we need the force parallel to the displacement. So the way that the force acts on the object is actually really important. It's not just about a force acting on the object. So we've got to look at the angle that it acts at. Okay, so now we've got the equation W equals F delta X cos theta. Remember, F is the force that's acting, which means that will be in newtons. Delta X is the displacement. And of course, we're using delta X because we're looking at displacement in the horizontal component this way, horizontally. Okay, that's fine. Then cos theta, theta is the angle of the force. Okay? Now, be careful here because theta is going to be a value from 0 to 90, or it's going to be 180, okay? It's not, we're not going to work with thetas of 120 and that sort of thing. It's going to be between 0 and 90 and 180. I'm going to talk about what those mean in a second. And of course, we've got to remember that work is a scalar quantity. Scalar means that it has magnitude only. We don't care about direction, but be careful here, please. It doesn't mean that it's only going to be positive. We get negative work as well, and you need to leave it as negative work. We'll explain what those mean in a second, okay? Now, we need to talk about network, because just because I'm doing work on an object, because there's lots of other forces acting on the object, doesn't mean that work, if I'm pushing a box up a hill, why I'd want to do that, I don't know. But if I was pushing a box up the hill and the box is going at a constant velocity, we'll actually find that I'm not doing any net work. I might feel like I'm doing work because I'm expending energy and I'm getting tired, but in real science terms, I'm not doing any work at all on the box, because as much energy and work I'm putting into the box to get it up the hill, gravity is doing work. It's negative work. Okay, I'm having to push against gravity, and friction is doing work. Friction is also a negative work in this case, because friction makes the surface in the box get hot. That's useless to me. Okay, so we've got to look at whether we get network. Now, the concept of network is this. It's calculated by applying the definition of work to each force acting on the object and then adding them all together, or, and this is the method I prefer, by calculating the net force acting on the object and using the equation. Okay, there's more than one way to do these. I'm going to do the way where we look at the net force, okay, because it makes it easier to decide on theta, okay, and it's always going to be a net parallel force, makes it much, much easier for us, and then we'll go from there. Now, work can either be negative or positive, and positive work means that we are increasing the energy of the system. So when I'm pushing a box, I'm giving it kinetic energy. That's positive work. Negative work is friction. Friction does negative work because friction takes the kinetic energy that I'm giving to the box and turns it into heat, or turns it into sound, or turns it into some other form of energy, which actually is quite useless for us. So it's taking energy out of the system as such. So it gives us a negative value. Okay, so this is really, really important. Please be careful if you we've been doing work in science curriculum for many, many years. And if you're using older textbooks, sometimes they would say to you, but work can never be negative. Yes, it can, because it represents energy. Remember, work and energy, say in electricity, are interchangeable. Because actually, if something has energy, we have the ability to do work. When we do work, we expend energy. So the two can be interchanged in a lot of ways, okay? There's a very important relationship between them. Plus, work is measured in joules and energy is measured in joules. So they're closely related, okay? So what that means is we need to start looking at some problems. Okay, now I've got a nice easy one to start off with, okay, and we're going to do this one bit by bit. We're going to start with the first question, and I'm going to only give you 2 minutes because I don't want you to spend too long on it, and I'm literally only wanting to do number A. It says to you a force of 200 newtons acts at 60 degrees to the horizontal, accelerates a box of 50 kilograms, placed on a horizontal plane, not place, for 100 meters. Calculate the work done by the 200 Newton force. In fact, you know what? I'm not even going to give you 2 minutes. I'm going to give you a minute, okay? Because I want to be able to go through this before the break. So you've got the question now, all right? You have a minute to see how far you get with this question. And your minute starts now. Oh, I can just hear the groans. No, we didn't have enough time. It's okay. It's all right. Let's do that one quickly together. Now, this is, and I've chosen the first questions deliberately in that we want to look at going from simple to more difficult. We don't start with difficult ones. So we have a 200 Newton force acting at 60 degrees, and we know, and I'll write it into the diagram, that the box moves 100 meters. Okay, so that's quite important. Now they say to us, calculate the work done by the box. Well, I know F, it's 200 by the 200 Newton force. I know theta. I have a mass, but for work at this point, the mass isn't important. And of course, the 100 meters is delta x. So now when we go back to our equation, which says to us that W, and now the subscript is very important, grade 12s. I can't begin to emphasize how important it is because we're going to be looking at work being done by lots of different forces. So you need to tell your examiner which force you're looking at. And yes, I know it's specified in this equation, but you're going to run into trouble if you sometimes put it and sometimes don't. So rather just put the subscripts all the time, and then you know you're okay. All right? So work is going to be done by the force times by the delta x times by cos theta. So my force is 200, so that's easy. My x is 100. And now I need to find the angle. And it's cos, but my angle here was 60. We did that earlier. Grade 12's not always, but they tend to use your special angles. Cos 60 is one of them, and it's a half. I'm not expecting you to remember that. It's one of those things you put on your calculator, and out we come with 10,000 joules. Now that's a lot of energy, it's a lot of work, but it was a big force that was put onto a big mass, and it went 100 meters. That's quite significant, okay? So 10,000 joules, I'm okay with that, and I'm not too worried about that value, okay? So grade 12s, what we're going to do is we're going to take a short little break, and then we're going to do more with this particular situation. We're going to add some stuff to it, okay? So we're going to take a couple of well, a little break, and then I'll see you in a couple of minutes. Okay, grade 12s. Now, your brain's had a bit of a break. Okay, so now we're going to stretch those muscles a little bit more. And we've done the first question to this. All right, same situation. I'm just going to remind you that it moved 100 meters. Okay, but now there's actually 3 more questions here. There's B. This one should actually be C, and that one is D. So now you're going to calculate the work done by gravity. I want you to calculate the work done by friction, if there's 25 newtons, and then you're going to calculate net work. All right, so you've got 3 things that I want you to calculate. You're going to use the same equation over and over again. Be careful with theta. Okay, so I'm going to give you 3 minutes because you've got 3 equations. I'm going to see how far you get. Okay, so you've got 3 minutes, and that time starts now. So, grade 12s, how did we do? Did we do okay? Do we think we did okay? Do you think we're struggling with the angles? Well, let's just see how we did. Did some of us look at our answer for B and go, there's no way it can be 0? Of course it can. Let's have a look. Okay? So now we're going to go to the work done by gravity on the box. Okay, so we look in the first part. So first of all, we're going to recognize something. Gravity acts down. Okay, so gravity is acting at 90 degrees to the object's movement. Still moving 100, that hasn't changed. But what we want to know is, what is the force of gravity? So now we're going to say to ourselves, well, the force of gravity must be the object's weight. Okay, so what we're looking at is, in my equation, I'm going to use the fact that Fg equals mg, mass times gravitational acceleration. We know this. So when I do work done by gravity, okay, so now this is where your subscripts are so important, because I'm going work done by gravity is going to be the force of gravity times the distance it moves times cos theta. Now, we're going to have to work out mg, okay? And you can write it as another equation. If this is going to help you, then you do this. You don't have to show me this step here, but this step is just for those that struggle in terms of writing it all out and figure out where we get the values from. So mass is 50, gravity is 9,8, this is 100, and cos is cos 90. Now, cos 90 is a special angle. Cos 90 is 0. So no matter what 50 times 9,8 times 100 is, it makes no difference. It's still going to be 0 joules. Why do I know this is okay? Because my object moved horizontally, not vertically. Gravity's acting vertically. For work to be done, the force applied, or the force we're looking at, must be parallel to the direction it's moving in, not perpendicular. It's moving this way. Gravity goes this way. So that's really important. Okay, so that's a nice question, actually. It's a nice one to put in there. Now they ask you, this was the next one, was if there's a frictional force of 25, calculate the work done by friction. Okay, so now we go fine. We'll go back here and we say, okay, I'm going to use pink. It's a pretty color. Now we're doing the work done by friction, little f. Okay, friction. That means I need to use the force of friction, delta x, cos theta. So we're using the same equation over and over and over again. Friction is 25. This is 100. And now comes the trick. This is really, 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 really important for you to get. Your object is moving this way, okay? Just go, when you're looking at it, it's hard because of the screen, and just go with it. So it's moving in this direction. We know friction always opposes motion. So my object's moving this way, but friction's moving this way. So friction goes underneath and it goes in this direction. So my object and my friction are at 180 degrees to each other. Friction is always at 180 degrees. It's in the opposite direction to motion. So over here, this gives me cos 180. Why that is important is because cos 180 is -1. So that actually means that I'm going to get a negative answer for work done by friction. Perfectly acceptable. Because remember what I said to you, friction causes energy to be used up. So the friction is negative because it's taking energy out of the system. Negative answer, not a problem. Now we say to you, calculate the net work done on the box. Now I want to show you there's two ways. The first definition of calculating network that we did said that we can calculate network by looking at all the force, by looking at the work done by all the forces and adding them all together. So we've done the fact that there was gravity, and we said that there was friction, okay, and we worked out all of those. So my net work is actually the work done by the applied force plus the work done by gravity plus the work done by friction. So the work done by the applied force was 10,000. The work done by gravity was 0. And the work done by friction was minus 2,500. So that means that we get 7,500 joules. You know what? On a question like this, that's the easiest way to do it in terms of calculating net work, because we led you. We made you calculate work done by the force, work done by gravity, work done by friction. But what if that was the first question I asked you and I told you what friction was? Okay, this is the other option. So this is your all. And both of these will be looked at. Best, or we can go, well, what is the net force acting on the object? And you know what? I don't need to consider the horizontal forces here because it's not moving horizontally. All I consider here when I look at net force is I look at the forces that are acting horizontally with the object. So that means I've got the applied force plus friction. My applied force was, hopefully somebody said, well, hang on, wait, Josie. I was about to put 200 there, and I'm hoping somebody was like, no, that would be wrong, because it would be, remember, your applied force is at an angle, okay? That means when I'm looking at the net force horizontally, what I actually need to consider is I need to consider the force that's moving in that direction. So in other words, I need the horizontal component, okay? And I'm hoping some of you are going to catch this. The horizontal component is the force times cos theta. Okay, can you see why I could go F delta X cos theta is my work done? Because F cos theta is the force that's applied at a 0 degree angle. Okay, so I'm hoping some of you caught that. So let's just put this in here. I don't want some of you to lose what I'm trying to tell you here. So this is actually F, and here I'm going to put the horizontal force just so you remember. F cos theta plus my friction. So that means this is 200 times cos theta. I'm by default making the direction to the right is positive, so friction is always going to be negative. It's minus 25. So watch, that gives me a net force of 75 newtons. But we're not done, okay, because we wanted net work. Net work then becomes net force times delta X times cos theta. My net force was 75, cos is 100. Now we've got to make a decision again, okay? Friction, remember, goes in the opposite direction. My object is sitting on here, and I've worked out the net force. I've taken the forward force, and I've taken the backward force into account, and I've got a resultant forward force. So my net force and the direction of motion are in the same direction. That means cos theta, well, theta is 0, okay? 0. Friction, 180. Apply net force in the direction that it's moving in, 0. So, and look here, 7,500 joules, because cos 0 is 1. Look at that. Doesn't matter which way around you do the question, okay? The second method that I did now is absolutely longer because of the way we asked the question originally. Because we led you in the steps, then yes, the second way is absolutely longer. But in a test or an exam, they're not necessarily going to ask you to calculate all the other little works first and then add them all together. Okay? So this is when I teach my own learners in my classroom, I teach this method as the preferred method for me, because I think you make less mistakes finding F net first and then applying it to the equation than by doing all the works, because sometimes you get all confused and you forget about what gravity does, and when we start adding, gravity's not always our friend. I'm grateful we have gravity, otherwise we'd be floating in the air, but this is a good thing. Okay, so I'm hoping you guys did okay with that. All right, so now, and it went very quickly, it's time for another break, and when we get back, we're going to look at the work energy theorem, and I can just hear the groans. But it's okay, we can do this, all right? So we're going to look at work energy theorem, but first we're going to take a little break, and I'll see you in a couple of minutes. Okay, grade 12s, are we ready for this? Last little bit, let's look at the work energy theorem. Once again, it's a definition. It's one of those things that I know you're going to end up getting, and it means you have to learn it. So, work energy theorem says to us, and there's two ways we can state it. The net work, or total work done, should be net work on an object is equal to the change of the object's kinetic energy, or the the work done on an object by a resultant or net force is equal to the change in the object's kinetic energy. What's really, 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 really important here is there has to be a change in kinetic energy. That means there has to be a resultant force, okay? That means there has to be a resultant force. Remember, F net equals ma, Newton's second law. If velocity is going to change, which causes kinetic energy to change, there has to be an acceleration, which means we need to have a net force. Okay, that's where this is coming from. Now, in terms of an equation, in symbols, W net equals delta EK, which is EK final minus EK initial. That's final kinetic energy, and this is initial kinetic energy. And remember, I'm so good at making this change colors. It's so pretty, and I think I spelled initial wrong, but we'll just go with it. And the EK, remember, is equal to a half mv squared. Don't forget the square. So what this equation essentially is telling me is that if I don't know anything about the forces that are acting on an object, it's okay if I know what happens to the object's velocity, okay? Because I can use the object's velocity to work out the net work. From there, I could always work out F net if I wanted to, or I could use F net, I could use this equation to work out a velocity. There's lots of ways of using this equation, but it's work net. Please be careful. Next week, we're going to talk about what happens with a non-conservative force if we add friction. All right, doesn't mean you don't use these in only frictionless situations, but it's net work. It's very important. So the subscript, very, very important. Okay, so let's look at a question. Okay, I'm going to go through it with you just to give you an idea of what's happening in the question, and I'm going to give you some time to answer it, okay? So we have a 3 kilogram block which slides at a constant velocity, okay, that's important, along a horizontal surface. It then strikes a rough surface, that means there's friction, causing it to experience a constant frictional force of 30 newtons, which is great. The block slides 2 meters under the influence of this frictional force before it moves up a frictionless ramp inclined at 20 degrees to the horizontal as shown in the diagram. Okay, so there's what we've got. So the block moves up a distance d up the ramp before it comes to rest. And I'm really putting you into it with this question as your first one, okay? So let me just help you here. This has got a frictional force over here of 13 newtons. Let's write this in. So you've got the diagram. Everything else is actually all you needed to know. And it comes to rest at the top. So here's the questions, okay? They are coming here, okay. So the questions say, show by calculation the speed of the block at the bottom of the ramp is 3. Then I want a free body diagram acting on the block direction parallel to the incline. And then I want to know the distance it goes. And can you hear the grounds? So I'm going to give you 3 minutes, okay? And we're going to see how far you get. So your 3 minutes start now. Okay, grade 12s. Let's see how you did. Okay, so the first question was to show by calculation I don't know why I've got that twice. Let's go here. Was to show the speed of the block at the bottom of the ramp is 3. So if we go back to our diagram, okay, here they said to us that the rough surface has a frictional force of 30 newtons, and when it hits the rough surface, it's going at 7. Now, there's nothing pushing it forward. There's a change in velocity. They are asking you to prove that it becomes 3 meters per second when it gets to the end of that, okay? You cannot assume it gets to 3. I have to prove it. So we look at it and we go, well, actually, the only force acting on the object for those 2 meters, for these 2 meters, is friction. So there is a change in velocity, which means there is a change in kinetic energy. So I can use the fact that W net equals change in kinetic energy. Now, the W net I'm going to use, the only force acting on my object is friction. So I'm going to say, well, I'm going to use friction, delta x, cos theta. And I'm going to go straight into the equation for kinetic energy. So it's final kinetic energy, which means I use the final velocity minus the initial velocity. Okay? Don't get too stressed about negatives. And in this section, when I substitute friction in, I don't make it a negative force because the theta is going to, the cos 180 will take that into account. All right, so be careful. Don't put negatives in your forces anywhere here, otherwise you're going to run into trouble. So my friction, they said, was 30. So this is 30. Delta x, it went for 2 minutes. And remember, it's friction. So this is cos 180. All fine so far. Now we have a half. I'm going to try and fit this all in without going completely off the script, off the side. So that's 3. My final velocity is what I'm looking for. And my initial is what I have. Okay? Now, just from a time point of view, grade 12s, I'm not going to solve all of this. I'm not going to show you how to solve this mathematically, okay? You can always go ask your maths teacher if you get confused from this point. But here, now, okay, I will show you because I think maybe I should. I'll do that. I changed my mind. I'm a girl. I'm allowed to. So, this is minus 60. This is a half, VF squared. And this is minus 73 and a half. Okay, now if I take the 60 over, okay, or the minus 73 and a half, whichever way around we do this, it's better to take the 60 over. Okay, we get, and I've done something 73, so I'm going to take the 73 over, so this gives me 13,5. From here, I would now divide by 1,5 on both sides, and then square root my answer. And you know what? You get 3. And it's 3 exactly. So I know I got the right answer. Yay, we're happy. First question done. Yay. Okay, next one. Now they asked you, and they did this one deliberately, is they now say to you, draw a free body diagram to show that all the forces acting on the block in a direction parallel to the incline while the block is sliding up the ramp. The block is sliding up the ramp on a frictionless surface. It's going to stop. It has to. Okay? The only force acting on this object which is going to act down, is actually gravity. And the force that's actually acting on it, parallel to the incline, is my parallel gravitational force. Now they wanted, when you look at the question, they say free body diagram, so we know it's a dot, of the forces parallel to the incline. All they want is FG parallel. Don't put FG in. Why have they asked you this? Because it's for the next question. Because now the next question says, calculate the distance the block slides up the ramp. So we go back to our equation. We go back here and we say, well, I know that it starts at 3 meters per second, gets to naught, and I want this distance. Only force acting on it, Fg parallel. So we go back here. It makes this a little more difficult to work out, but I'm going to show you how we're going to work it. So I'm actually going to break this down, but I want you to see the process. So we go, I know I'm going to need to use W net, and I'm doing it on the side here for a reason, which is delta EK. Now, my W net would be the work done by friction. Not by friction, by the gravitational force, which actually means if I'm going to use the incline's going to be easier if I use the parallel force. That's why they made you work out, well, draw the free body diagram, because what I actually want is I want to use Fg parallel delta x cos theta. Delta x is d, and then I can do a half mvf squared minus a half mvi squared. How do we work out Fg parallel? Well, if we go back to the diagram, okay, let me do it here, it'll be easier. So there's my Fg, and I do it this way when I draw my angles. Fg parallel is here. That angle there is the angle of the slope, which is 20 degrees. It's opposite. So Fg parallel is Fg sine theta, okay? Now, I've just got a space issue in that, and you would never do this separately. Well, you can do it separately, but because of space, I'm actually going to add it into the equation, okay? So now watch what I'm going to do here. This is actually Fg sine theta. I'm going to go delta x cos theta. From here, it's now a substitution problem. So Fg is mass times gravity, and the block was 3 kilograms times 9,8, and here it's sine 20 degrees. Delta x is d, so I'm going to change it to d now, because now I'm doing the substitution. Ooh, now comes the fun part. The block is moving up the slope, gravity's pulling down, opposite direction. It's the same as friction. That means 180 degrees. Okay? Now over here we've got a half, and I'm going to show you this, though if you recognize it as 0, you don't have to put it in. It stops when it gets to the top. And here, that's 3, and the initial velocity is 3 now. Grade 12s, if you didn't get the first question, which said prove that it's going at 3, don't stress about it. For this question, you assume it's going at 3. Because actually, they're not going to say to prove that it's going at 3, it's actually going at 2. All right, they won't ever do that. Whatever they ask you to prove is what you should get. Now, if you don't get there, don't use your answer, because they won't carry it down. You need to use the answer you were supposed to get, okay? So now, we type all of this into our calculators, and 3 times 9,8 times sine 20 is actually 10,6. Cos 180 is minus. Okay, so that's D. And a half times 3 times naught is naught. Then we've got a half times 3 squared. 3 squared is 9. A half times 3 is 1.5. That gives me minus 13,5. Okay, you're just going to have to believe me on that one. I promise I didn't do that in my head. I do have it all written down and worked out. So now, how do I know I've done this correctly? I'm going to get a positive distance. So now I'm going to go minus 13,5 divided by minus 10,6, and I get 1,27 meters. Okay? Don't get too stressed about the distances. Remember, it's actually quite the force isn't very big. It's 10,6, so it's not going to go very far distance. And it's going against gravity, so it's not doing anything useful. It's got to stop eventually. If they had added in friction, then we can do exactly the same thing. All right, so if we had added in friction in this, remember friction would have gone up in the opposite direction to gravity. Okay, no, I'm lying. friction would have gone down, friction would have helped gravity. Okay, so your net force would have been gravity, the parallel force plus gravity. They did in their test for the grade 11s and they hated it. So be careful with that, grade 12s. All right, now what you need is go home, think about this, think about the work energy theorem. We're going to add to this next week. We're going to see what friction does. We're going to add a little bit of energy to it, and then we're going to do some power. Okay, we've done a lot today. It doesn't feel like it, but we really have, and I'm hoping we've cleared up some issues for you grade 12s. And I am actually left with nothing left to say, which is quite unusual. So hopefully you all have a good week, and I will see you next time.